study homomorphism. Homomorphism also means topological equivalence. A function f which is bijective means which is 1, 1 and onto between two topological spaces x and y with the property that f and f inverse are continuous, where f inverse is a mapping from y to x. If f is bijective and f inverse are continuous, then the function f is called a homomorphism. If there exists a homomorphism between x and y, then x and y are called homomorphic spaces, or we say that x and y are topologically equivalent. In this case, we write like this. It means x and y are topologically equivalent, or x and y are homomorphic spaces, or there is a homomorphism between x and y. Another common notation is like this. So we have one lemma. Being homomorphic is an equivalence relation on any set of topological spaces. Number 1, for each space X, the identity function means Ix equal to X for all X belonging to X is a homomorphism. Number 2, if F is a homomorphism, then F inverse is also a homomorphism. If F is a homomorphism and G is a homomorphism, then the composite function Z of F is also a homomorphism, where G of F is a mapping from X to Z. One more lemma we have. Let F is a mapping from X to Y be bijective, means it is 1, 1 and onto between two topological spaces X and Y. Then the following are equivalent. Number 1, F is a homomorphism. Number 2, a set U which is a subset of X is open in X if and only if the image Fu which is a subset of Y is open in Y. Number 3, a set V which is a subset of Y is open in Y if and only if the pre-image F inverse V which is a subset of X is open in X. So to show that F is continuous, we need to show that if V is a subset of Y, then F inverse V, which is a subset of X, is open. If we say that F inverse is continuous, it means that if U is a subset of X and it is open, it means Fu, which is a subset of Y, is also open. Now each U which is a subset of X has the form U equal to F inverse V. And for a unique V subset of Y with Fu, we can write this as F of F inverse V. F of F inverse V means V. It means Fu equal to V. Hence, to say that F inverse is continuous, it also means that F inverse V, which is a subset of X, open implies that V which is a subset of Y is also open. It means 1 and 3 are equivalent. Means if F is a homomorphism, then a set V which is a subset of Y is open in Y if and only if the pre-image F inverse V which is a subset of X is also open in X. If in this we replace F by F inverse, then it shows that 1 and 2 are equivalent. Means if F is a homomorphism, then a set U which is a subset of X is open in X if and only if the image Fu which is a subset of V is open in Y. In other words, F is a homomorphism if and only if the image function F from Px to Py induces a bijection from a topology on X on the topology Y. Or in other words, if the pre-image function F inverse, which is a function from Py to Px, induces a bijection from the topology on Y to the topology on x. Here we want to mention that any property of x that can be expressed in terms of its elements and its open subsets is called a topological property. If f is a function from x to y is a homomorphism, then any topological property of x is logically equivalent to the corresponding topological property of y obtained by replacing each element x belonging to x by its image fx belonging to y, and each open subset u of x by its image fu, which is a subset of y. Such topological properties are thus preserved by homomorphism. We have one example. For instance, being a finite topological space having the discrete, trivial or cofinite topology, or being a Hausdorff space are all examples of topological properties. So if X is a Hausdorff space and X is homomorphic to Y, then Y is also a Hausdorff space. Suppose we have two closed interval x equal to 0, 1 and y equal to AB, where A is less than B, each with the subspace topology from R. Then 0, 1 and AB are homomorphic. One example of homomorphism f from 0, 1 to AB is given by the linear function fx equal to a plus b minus a into x. We can write it like this. If we open the bracket, we get a plus bx minus ax, and if we take x common, a common, then we can write it as 1 minus x into a plus bx or xb. The inverse function f inverse from ab to 0, 1 is given by the linear function f inverse y. If we put it y and solve it for x, we get f inverse y equal to shift this to this side, y minus a, and this will come to denominator b minus a. So y minus a upon b minus a. So inverse function f inverse is given by the linear function f inverse y equal to y minus a upon b minus a. Here f is continuous. Clearly f inverse is also continuous. Hence any two closed interval a, b and c, d are homomorphic for a less than b and c less than d, as we have seen in this example, because we have shown by taking this linear function that f as well as f inverse are continuous, and f is a 1 1 and onto mapping. So it means two closed intervals are homomorphic. Any two open intervals of the form AB or A infinity or minus infinity B or minus infinity to infinity are homomorphic for A less than B. First of all, we consider 0, 1 and AB. 0, 1 and AB are homomorphic, and we write 0, 1 is homomorphic to AB. Suppose f is a linear map from 0, 1 to AB given by, again I have taken the same example, fx equal to a plus b minus a into x, which can also be written as 1 minus x into a plus xb if we multiply by x and then take a common. Clearly this is a homomorphism with f inverse which is a mapping from AB to 0, 1 given by f inverse y equal to y minus a upon b minus a. This we can obtain easily by substituting fx equal to y and then simplifying it for the value of x, because if you substitute here y, so if you shift a to this side, then we will get y minus a, b minus a will come to denominator. So x is equal to y minus a upon b minus a. It means f inverse y is equal to y minus a upon b minus a. Also 0, 1 and 1 infinity are homomorphic. For this, we define the function f 0, 1 to 1 infinity given by fx equal to 1 upon x. That this function is a homomorphism because it is also continuous in this interval with the inverse f inverse which is a mapping from 1 to infinity to 0 to 1. Here if we substitute fx equal to y, then y is equal to 1 upon x means x is equal to 1 upon y, means f inverse y is equal to 1 upon y. Also using fx equal to x plus c or fx equal to minus 1 minus x, it is easy to see that 1 infinity is homomorphic to a infinity and minus infinity to b is homomorphic to minus b to infinity for any a and b. Finally, the function f from minus 1 to 1 to r is given by fx equal to x upon 1 minus x square is a homomorphism, means minus 1 1 is homomorphic to r. To find the inverse, we write the equation x upon 1 minus x square equal to y. Because fx is equal to x upon 1 minus x square, we have replaced fx by y. To find the value of x, first of all we cross multiply it. So means x is equal to y to x is equal to y minus yx square. If we shift all the terms to one side, we get yx square plus x minus y. This equation is quadratic in x, which we can easily solve for x, where x belongs to minus 1 to 1 as a function of y, which is the element of r. So if we solve this equation is quadratic in x. So then f inverse y is equal to minus 1 plus under root 1 minus 1 plus 4y square upon 2y. Because we can compare this equation by ax square plus bx plus c equal to 0. Here a is y, b is 1, c is minus y. In this case, x is equal to minus b plus minus b square under root b square minus 4ac upon 2a by Sridharacharya method. So here b is minus 1 plus minus I have not written under root b square means minus 1 whole square 4ac because here it is minus, so minus minus plus 4y into y 4y square upon 2y. If we rationalize this function, means multiply and divide by 1 plus under root 1 plus 4y square, we get 2y upon under root 2y upon 1 plus under root 1 plus 4y square. Because in the denominator, in that case, multiply minus 1 plus under root 1 plus 4y square by 1 plus under root 1 plus 4y square will be minus 1 plus 1 plus 4y square. Minus 1 and 1 will cancel out. Under root 4y square is 2y. So in the numerator we have only 2y. In the denominator we have 1 plus under root 1 plus 4y square. It is well known that this function f, which is x minus 1 minus x square, and this f inverse y, which is 2y upon 1 plus under root 1 plus 4y square, are continuous function. Hence r is homomorphic to minus 1 to 1. Therefore, to any interval ab. One more example, if we define tangent to be minus pi by 2 to pi by 2 to r and the tangent inverse to be r2 minus pi by 2 to pi by 2 are both known to be continuous, hence mutually inverse homomorphisms. One more example, suppose we consider x equal to interval consisting of 2 points a and b, and suppose TA is equal to phi a and x and TB equal to phi b and xb, two topologies. Then these two topologies are equivalent, means these two topology xt a topological space is equivalent to xtb topological space, means xTA is homomorphic to xTB by the function f, which is a mapping from x to x given by fa equal to b and fb equal to a, which is equal to its own inverse. Note that image of f, which is a mapping from px to px, takes ta bijectively to tb with inverse given by the pre-image f inverse from px to px. In other words, any statement S about the elements and open sets of xTA corresponds to a logically equivalent statement S dash about the elements and open sets of xTB given by interchanging the roles of A and B. Note also that the identity function I from xTA to xTB is not homomorphism because it is not even continuous. Thank you.